Optical, single mode, multimode. The physics of light, an in-depth analysis of optical fiber. When we transition from copper-based networking to optical fiber, we are fundamentally shifting the medium of communication from the flow of electrons to the propagation of photons. In a copper wire, data is represented by fluctuating electrical voltages, which are subject to the laws of resistance, capacitance, and electromagnetic interference. In contrast, optical fiber uses pulses of light, essentially high-speed laser or LED blinks, to transmit binary data. Because light travels at nearly 300,000 kilometers per second and is not influenced by magnetism, fiber optics represents the pinnacle of modern networking performance, offering bandwidth and distance capabilities that copper simply cannot match. The anatomy of a fiber strand, total internal reflection. To understand how light stays trapped inside a hair-thin strand of glass, we must look at the physical construction of the fiber itself. A single fiber strand is composed of 3 concentric layers, each serving a vital role in the data transmission process. At the very center is the core. This is the physical pathway for the light, typically made of extremely high-purity silica glass. The core is so clear that if you had a block of this glass miles thick, you could see through it as clearly as a window pane. Surrounding the core is the cladding. This is also made of glass, but it has a different refractive index than the core. This difference is the secret to fiber optics. When light traveling through the core hits the boundary of the cladding at a shallow angle, it does not pass through. Instead, it is reflected back into the core. This phenomenon is known as total internal reflection. It allows the light to zigzag or spiral down the fiber, even when the cable is bent around a corner, without leaking out. Finally, the cladding is protected by a plastic buffer coating and an outer jacket. These layers provide no optical benefit but are essential for mechanical strength, protecting the delicate glass from moisture, bending stress, and physical crushing. Single-mode fiber, SMF, the long-distance engine. Single-mode fiber is the high-performance variant of optical cabling, designed for maximum distance and speed. The single-mode designation refers to the fact that only a single mode or path of light can travel through the fiber at one time. Core construction and light source. The core of a single-mode fiber is incredibly tiny, typically only 8 to 10 microns in diameter, roughly 1/10 the thickness of a human hair. Because the core is so narrow, the light cannot bounce around or reflect off the walls in multiple directions. Instead, it travels in a virtually straight line down the center of the fiber. To inject light into such a small opening, single-mode systems require a highly focused, coherent light source, specifically a laser. Performance characteristics. Because the light travels in a single, straight path, it does not suffer from signal dispersion. In other words, the light pulses stay sharp and distinct even after traveling for miles. This allows single-mode fiber to carry data over incredible distances, often up to 40 or 50 miles, without the need for a repeater or an amplifier to boost the signal. Use cases and costs. Single-mode is the standard for wide-area networks, WANs, telecommunications backbones, and undersea cables that connect continents. However, this performance comes with a higher price tag. While the cable itself is relatively affordable, the laser-based transceivers required to light the fiber are much more expensive and generate more heat than the LEDs used in other systems. Multimode fiber, MMF, the local area network specialist. If single mode is a one-lane highway, multimode fiber is a wide, multi-lane tunnel. It is designed for shorter distances, typically within a single building or a data center campus, where cost-effectiveness and ease of connection are more important than extreme distance. Core construction and light source. The core of a multimode fiber is significantly larger than that of single mode, usually 50 or 62.5 microns in diameter. This larger opening makes it much easier to couple light into the fiber, allowing for the use of less expensive light sources like light-emitting diodes, LEDs, or vertical cavity surface-emitting lasers, VCSELs. The challenge of modal dispersion: because the core is so wide, the light doesn't just travel in one straight line. Instead, different modes of light enter the fiber at different angles. Some light takes a straight path down the center, while other rays bounce off the cladding walls repeatedly. Because the light that bounces takes a longer physical path than the light going straight, the pulses begin to spread out as they travel. This is known as modal dispersion. If the cable is too long, the end of one LSE will begin to overlap with the start of the next pulse, causing the data to become garbled and unreadable. This is why multimode fiber is strictly limited in distance, usually to about 550 meters for 10 gigabit speeds. Step index versus graded index: to fight modal dispersion, modern multimode fiber uses a graded index core. Instead of a sharp step between the core and cladding, the refractive index of the glass changes gradually from the center outward. This causes the light rays that bounce toward the edges to actually speed up, while the light in the center slows down. This compensation helps all the different modes of light arrive at the end of the cable at roughly the same time, significantly improving the bandwidth. Comparing the two, a technician's perspective. When deciding between single mode and multimode, a technician must weigh several factors: distance, bandwidth, and total project budget. Distance: single mode is the clear winner, capable of spanning kilometers. Multimode is generally restricted to hundreds of meters. Bandwidth: while both can handle 10, 40, or even 100 gigabits per second, single mode has a virtually infinite bandwidth potential because it does not suffer from modal dispersion. Cost: multimode systems are significantly cheaper overall. Because the core is larger, the connectors do not have to be as precisely aligned, and the LED-based electronics are much more budget-friendly than the high-precision lasers needed for single mode. Color coding: in the field, you can often tell them apart by the color of the outer jacket. In the United States, single-mode fiber typically has a yellow jacket, while multimode fiber is usually orange for older Ohm 1 or Ohm 2 or aqua for modern, laser-optimized Ohm 3 or Ohm 4. Why fiber is superior to copper? Regardless of whether it is single mode or multimode, fiber optics offers three massive advantages over copper cabling that make it indispensable in modern IT infrastructure. 1. Immunity to interference: because fiber uses light, photons, rather than electricity, electrons. It is completely immune to electromagnetic interference, EMI, and radio frequency interference, RFI. You can run a fiber optic cable right alongside a high-voltage power line, inside an elevator shaft next to a massive motor, or through a factory floor filled with heavy machinery, and the data signal will remain perfectly pure. 2. Enhanced security: copper cables emit small electromagnetic signals that can be sniffed or tapped into by hackers without even touching the wire. Fiber optics, however, does not radiate any signal outside the glass core. Furthermore, it is incredibly difficult to tap a fiber line without physically breaking the glass, which would cause an immediate, detectable drop in signal strength, alerting the network administrators to a security breach. 3. Weight and size: fiber optic cables are significantly smaller and lighter than copper cables of the same capacity. A single fiber trunk the size of a finger can carry as much data as hundreds of thick, heavy Cat6 copper cables. This is vital in crowded data centers where cable management and airflow are major concerns.